The next conjugate addition reaction that I'm going to show you guys is called the Stork Enamine synthesis. And the Stork Enamine synthesis is just a variation of the Michael addition reaction. It is a Michael addition reaction that just uses a different nucleophile. So what I'm going to do first is show you the mechanism, or not the mechanism, the overall reaction. And then we're going to talk about how it's different and why it works. So this will start with any aldehyde or ketone. And this is going to end up being our nucleophile, which is this, an aldehyde or a ketone is not one of the acceptable nucleophiles for the Michael reaction. And the first thing that we're going to do is convert that aldehyde or ketone to an enamine. So we haven't practiced this for a couple chapters, but this is just using a secondary amine with acid. And it's going to give us an enamine. We're not going to draw it here. We'll draw it eventually. And then we are going to bring in some sort of Michael acceptor. So just another one of those conjugated, usually carbon-carbon double bond conjugated with a carbon-oxygen double bond. So this would be any Michael acceptor. And still not going to draw what we get yet. And we're going to do step 3 here with H3O plus. And we will end up doing, let's number our Michael carbons, 1, 2, 3, 4. So we're going to end up doing what appears to be a normal Michael reaction. I'm going to start by drawing that Michael acceptor and numbering those 4 carbons, 1, 2, 3, 4. And we are adding the aldehyde or ketone to carbon number 1, exactly like we would add any sort of Michael donor to that exact same position. So let me kind of mark this guy so you can see where he ended up. So the reason that we would use a Stork enamine synthesis instead of a traditional Michael reaction is that simply that we can't use regular aldehydes or ketones in the Michael reaction. Regular aldehydes and ketones cannot be used in the Michael reaction just as is, because they are too reactive. So let's scroll back up to the regular Michael reaction. In the regular Michael reaction, the nucleophile that we're looking at is a negatively charged nucleophile. And here it is, here's one version of it. So this is it's an enolate. In all of these reactions, negatively charged nucleophiles, an enolate. So if we had a regular aldehyde or ketone and we converted it to an enolate, that enolate from a regular aldehyde or ketone is too reactive for the standard Michael reaction. Instead of going after carbon number 1, they would react with the carbonyl carbon. Instead of reacting further down the carbon chain, I'm going to call that reacting at the Michael site. That's my made-up term. The Michael site is reacting at this, what I'm labeling carbon number 1, reacting out here. So if we have a regular aldehyde or ketone and we turn it into a negatively charged nucleophile, an enolate, that enolate, because it's not being stabilized by multiple carbon-oxygen double bonds, it's not very stable, it's just going to go after that Michael acceptor and it's going to hit it right at the carbonyl carbon. We need, in order to be able to do this Michael addition reaction successfully, we need to have a really, really weak nucleophile that is not going to be very motivated to react. And so it will instead come out and attack at carbon number 1 away from the carbon-oxygen double bond. So let's take a look at exactly what this would look like, kind of step by step, in the reaction, and then we'll look at a couple of examples. So this is going to be not a mechanism, not like an arrow pushing mechanism, but more like a mechanism than what I drew originally, generic reaction. So first thing that we're going to do is make the enamine with whatever aldehyde or ketone we're working with. And that enamine is going to look like this. This particular enamine will look like this because I'm choosing to use a couple of methyls on my nitrogen. And really, it doesn't matter what the R groups are on your nitrogen because they're just there for a second and they go away. So you just choose whatever R groups you want, whatever you happen to have available to you in the lab. Now, this molecule, this enamine, does have a resonance structure that we can draw that shows its reactivity. So we can move that negative charge down onto the carbon. We can move a lone pair of electrons down onto the carbon. And then that particular, so I should probably put that in some brackets, that particular version of the enamine is easier to visualize the next step of the reaction. So now we're going to bring in our conjugated molecule, and you can see that it's going to attack out there at the end, move some electrons around. So here is where it's really resembling a traditional Michael reaction. And we're going to get, first there's the Michael acceptor drawn all nice, and we need to add, kind of going to look ugly originally, we're going to add that enamine to it. Spectacular. And I forgot a positive charge on my nitrogen with the extra bond. There you go, buddy. So there's our intermediate. And so normally in a regular Michael reaction, the next thing that we would do, the H3O+, so we talked about how our next step, we're going to move these electrons down. We're going to move these electrons, not there, out to grab one of the hydrogens from the H3O+. And also, simultaneously, that H3O+ hydrolyzes the enamine and converts it back to the ketone. So in addition to finishing up the Michael addition part of the reaction, we are going to return the original carbonyl group from the original ketone. It all comes back. So the H3O+ also converts enamine back to a ketone or an aldehyde, whatever you are working with. And again, these reactions are just, when you see them on paper, and it's just so easy to not recognize them, at least for me. Like I look at them and I'm like, what in the heck is this even asking me to do? So here's a ketone with a secondary amine. Step 2, a conjugated carbonyl. Step 3, an acid, H3O+ or H+. I see this and I'm just like, I don't know what you're asking of me, and I don't know what I want. I don't know what you want from me. So what we're gonna do, what I'm always trying to remember to do, is take my Michael acceptor 1, 2, 3, 4, 1, 2, 3, 4, and I am creating a bond to what I've labeled as carbon number 1, and that bond is going to be made from one of the one of the alpha carbons of the ketone or aldehyde, and hopefully it's symmetrical and you don't have to think about which one is actually making the bond. You got to be careful that you get that carbonyl group in the right spot. There it is. This is not easy. This is a hard reaction. Let's look at one more example. Sometimes, because the amine doesn't actually matter, sometimes it'll just say R, because it really doesn't matter. And let's do like trying to make something up in the fly here. Let's do this guy. And then more acid, step 3. So draw that Michael acceptor. I'm going to draw the whole thing, even though I know I have to get rid of one of those double bonds. Number your carbons, 1, 2, 3, 4. And where are those carbons? 4, 3, 2, 1. We are going to be creating a bond to carbon number 1. And that bond is going to be to one of our enolate carbons. And when it's asymmetrical, you're going for the most substituted. So, doot, 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 doot. There it is. Whew, that's tough.